Hello everyone. I welcome you all to this the 30th day of MATLAB Simulating Masterclass series. This is Malaipan from Pantech Solutions. Our today's topic is hardware design of three-phase induction motor using Arduino microcontroller. So in this topic, we will discuss about what is the basics of induction motor, and then what is the programming structure, and what are all the things needs to be considered in the hardware sessions. And finally, we will see the hardware demonstrations. And so this is today is the last date of MATLAB Simulating Masterclass series. So far we have covered basics of power electronics and power converters, inverters, and designs of sensing circuits and other topics. See, called actually here based on the MATLAB Simulink. So we have covered so far matrix converter, grid tie inverter, and multi-level inverters, and Simulink based motor control solutions for BLDC, PMSM, and MPPT solutions and all. So today is the last date. Actually, again you have an important announcement. Please engage with the entire session so that you can use that benefit to your further research purpose and all. And today, the 30th day, so I wish you all to get the entire thing. I hope I have transferred the things to you as much as possible. So you will enjoy the sessions. So please keep engaged with the entire session, today's session. And again, during the end of the session, I will give you some instructions how to proceed further. Again, so far we have finished the 30 days, right? So after 30 days, what we have to do, and then how we can proceed further, and how we can continue the research in this power electronics segment, and what is the next step of this MATLAB Masterclass series. So those things we will discuss in detail. Keep engaged with the entire session. And from our application point of view, see, this is the basic application block diagram. Input, power circuit, load, and the controller. So today we are going to discuss all the components. Actually, so far we have discussed, part by part. Like some session we have discussed only the input part and only the output part and only the power circuit. So now we are going to discuss entire integration of the block diagram. See, actually in the hardware part, so we need all the sessions, all the models called input model, how much input we should choose, and then if we choose some input, then how much will be the output. So like that we will discuss in detail. So before starting the speed control mechanism for the induction machines, so we should know about the induction motor principle. So this is the basic induction motor principle. It has a variety of types called slip ring and then squirrel cage induction machine. It will work based on the mutual induction principle. So this is basic theory. Whenever you apply the supply to the stator, then based on the mutual induction principle, the rotating flux will generate at the rotor side due to the stator rotating flux. So due to this, because the rotor is always mounted on the free end bearings, so ball bearings. So due to that rotating flux at the rotor side, then the rotor will receive energy to rotate it. So anyhow, it will try to catch the synchronous frequency, but it will not be. So it will run at a slip speed. Right, so this is the basic construction, a basic working principle of the induction motor. So whenever you apply three-phase voltages, then the green color is the resultant flux which is available on the rotor side. Similarly, the violet color wave is a rotating flux at the rotor side. So due to this principle, so the rotor try to rotate from its standstill position. And again, this is the mechanical movement of the rotor machines. And so the type of the machine, single phase and then three phase. Again, the three phase variety of squirrel cage and slip ring machine. And in the single phase, split phase, capacitor start run, then capacitor start and capacitor run induction machine. So like this, these are the basic types of the machine. So these concepts we have discussed. So in the previous sessions also. And if you take a hardware block diagram, See, earlier we have seen the block diagram that is called single line block diagram. So now we need to discuss about some more detail about the block diagram. So what it is. See here, anyhow we are going to use the induction machine, right? See here, this is the induction motor part. So this is the induction motor part. So now we have to power up the induction motor with the help of three-phase inverter. So for this inverter, we have to supply DC bus voltage, DC voltage. That is a DC bus voltage. Either we should get from the conventional power, or else we have to apply from the battery source. Right? So now we took a conventional power. So for the conventional power will be the AC power. So it will be 230 voltage AC. So here we have to put a isolation transformer or step down transformer to trap the power from the conventional power source. So for that one we are using this power transformer, and again we have to feed the power to the inverter as a DC, right? So for that one we have to use a bridge rectifier. So this will be the uncontrolled bridge. And again the controller is the Arduino microcontroller. So for the Arduino microcontroller we have to give the power supply via 5 voltage, or else from computer you can feed the power. Similarly, the driver circuit. So this is the driver circuit which is help the microcontroller from the faulty current of the inverter side. So it will provide you the excellent isolation along with the amplification as much as the current required for to trigger up the MOSFETs or IGBT. And suppose if we take a rating, how much rating we should take? See, for example, three-phase induction motor. So there are two conditions. One is called how much load you are going to load to the motor. Similarly, suppose if you are running the motor at no load speed, only thing you are going to change the speed. So now we choose the case 2, no load conditions. So there is no any load applied to the motor. Second thing, we are going to just change the speed. So we are going to try to understand the concept of speed control mechanisms. So for that one, again you have three options. See, in that case, if you are going to run at a no load speed and various speed rating, then you can choose the power supply accordingly, because the motor will start from the 40 voltage AC onwards. If you apply single phase, phase voltage is about 40 voltage, then the motor will start to run, but it will not run at the rated speed, right? So for that one, if you take a option 1, so called if you apply the 230 voltage from the main supply. So if you take a isolation transformer, if you are getting a 230 voltage and a 6 ampere, then so you will get a 325 voltage DC at the rectifier end. So if you apply this 325 voltage at DC side, then you will get the 220 voltage AC at the transformer side. That is a AC phase voltage. If you measure line voltage, it's about 400 voltage. Right? So this is the option 1. Then option 2, you can take a 230 instead of 230 voltage, you can take a 110 voltage with a sufficient current rating. So 2 ampere is the maximum. 2 ampere is enough to run the machine at no load speed. And so if you take a 110 voltage, then you will get a 155 voltage at the DC terminal bridge rectifier, and similarly again you will get a 110 voltage at the AC terminal output. This is the output of the inverter. So still this inverter also will work. And so here now you have to increase the speed as much as possible. And again, a third option is, again you can take a 50 voltage input and with the 2 ampere, that is the maximum 2 ampere. So by choosing these options, we can reduce the project development cost. Because if you are going for the high power transformer, then you have to buy that costly transformer. So these are just an option. You can choose whatever you want. And likely, so 50 voltage also you will get. So here we can if you change the frequency of the output voltage, then we can get a variable speed control method. So for that one, again the driver circuit needs a separate power supply. So that we will discuss in detail about the driver side. And Arduino microcontroller. So here the Arduino microcontroller is there. So this controller will have it needs separate power supply. So to trigger up the microcontroller, again you can feed the input to the microcontroller. So if you as a input, that is called to change the frequency, and you can input assign two switches. So one switch for frequency increment and then to another switch for frequency decrement. So like that we can program. Okay. Right. So these are the power rating of the block diagrams. And similarly, for the step down, the powers of rectifier unit. So this is the very first block. This block. So up to here, right? So this entire unit. So this is a rectifier block. So here we have to feed the 230 voltage input, and the transformer, based on your options, it will work and it will give you the power voltage. And so after the transformer, we have to keep one bridge rectifier. So this is the bridge rectifier. In real-time applications, you can get a single device as a for combination of 4 diodes. So either 5 ampere device or 10 ampere device or 15 ampere device or 50 ampere rectifier. So these are called uncontrolled rectifier. So its operation we will discuss in the next slides. And similarly, this is a filter capacitor to regulate the DC output voltage. So why we have to use this step down transformer? So here we are going to study the speed control mechanism, right? So in that condition, we have to keep the CRO probe at anywhere in the hardware circuit, right? So if you connect the hardware CRO probe to the hardware circuit, then that neutral point, and if you don't have use this transformer, that conventional power source neutral will get short circuited. Because the CRO will have a 3 pin. So one is the phase, neutral, and the earth pin. Somehow, so the short circuit will happen between neutral and earth. So due to that, during that testing, so the main power supply will get short circuited. So to avoid that one only, we are suggesting you to choose one transformer so that we can play very well in this hardware prototyping circuit. Otherwise, we cannot. We have to use the current probe to measure the current the current measurements and the voltage measurements. So in the CRO we have to use a different probe. So that is called isolation probe. We have to use. And similarly, so this is the bridge rectifier operation. So whenever the positive voltage is here, so two diodes will take place to get output voltage in the positive direction. So let us understand the concept of working principle. Yeah, see here, this is the very basic circuits. Here 4 diodes are there, and the input is AC and output is connected. That is, as per our circuit, the output is this. Our load is as a inverter load. So the entire part will be the inverter load. So once if you turn on the power supply, then the T1 and T2 will take place to convert AC voltage to DC, and the current flow will be like this. Similarly, so during that negative period, the T3 and T4 will take place to convert the DC, negative DC to, negative AC to positive DC. So at the time we will get the entire DC voltage. See here, so if you run this video entire, then you will get a complete converted DC voltage. So if you apply filter, then we will get a straight line of the DC. So like this, this is the working principle of single phase rectifier. And 3-phase rectifier. See, after the second block is our inverter block, right? So now we have to understand the working principle of the inverter. So then only we can generate a pulse width modulate PWM signal from the Arduino controller. If you don't have, without working knowledge in the working principle of the inverter, then we cannot generate a PWM from this microcontroller. So let us try to understand the working principle of the inverter. See here, it has a 2 type of operating modes. One is called 180 degree mode, and another one is a 120 degree mode of condition. So the output the output of the inverter must be pure sine waveform. So here we can understand the concept of modes. See here, so up to 360 degree. up to 360 degree. If you take any 60 degree, so this is a 60 degree, and similarly then another 60 degree. So this is a 60 degree. See here, if you take again, see here. See, whenever the phase voltages crosses the 0 degree, so let us consider this is a mode of we can separate as a modes, right? So why we are calling this as a single mode in the sense, so during this entire period, the voltage of any waveform will not cross over it. So either if you take this is let us consider this is a mode 1. So during this mode 1, phase phase 1 and phase 3 are the positive one, right? And during that mode 1, phase 2 is a complete negative. So till the entire period of the mode 1, the phase the positive and the signs of these voltages are same conditions, right? Similarly, then we are getting that mode 2. So in this mode 2, here in mode 1, that the phase 3 was the positive, and then in mode 2, the phase 3 is the negative, right? So like that, like this, we are separating the modes, right? See here. So let us take this diagram. So in the dark blue color, so the entire period is the positive voltage of the phase A, and this is the light blue color is the negative phase voltage of the phase A. Similarly, phase B and phase C, right? So if you take each and every 60 degree, so this is a mode 1 and mode 2, mode 3, mode 4, mode 5 up to mode 6. Right. So now we have to understand, we have to identify at each and every mode what all the switches are in on conditions and what all the switches are in off conditions. Then, see, during the mode 1, during the mode 1, Q1 and Q6 will be the on state conditions, and during the mode 2 and Q2, that is the switch 1 and then switch 2 is the turn on condition. So like that it will rotate. So now we have to generate a pulse width modulation. So from this table, right? So we will detail explanation will be in the coding part. And to fabricate the hardware, see, so far actually we can use if you are going to use at no load conditions, that IR of 250 MOSFET is enough with the heatsink is enough. And sometimes for no load conditions, heatsink also not required, but the proper manner you have to use the heatsink. And operating frequency, maximum operating frequency is the switching so 25 kilohertz, because some transients will be there. The fundamental frequency will be the 50 hertz, but the maximum we have to choose the driver component for the maximum switching frequency, so that we can have full flexible frequency operating range. And so this board will have in our website, so you can get it from our website also. So this is that board. In this board, for 6 MOSFETs are there. So this is the MOSFET along with the heatsink, and so this is the input. Here we can feed the input. So it will handle up to 230 voltage maximum. So this is the 230 voltage up to 5 ampere. You can handle. You can operate this with this board. And this is the full bridge rectifier. This is the full bridge rectifier. Then filter capacitor. So here the filter capacitor can be 1000 microfarad, 200 voltage. If you have a 400 voltage capacitor, then you can keep single capacitor. Else you have to use 2 capacitors. Sometimes in market you won't get the entire range of the capacitance. 1000 microfarad, 200 voltage, and then 400 voltage. So 2 ranges are available. So if you use a 400 voltage, you can get single capacitor. If you have only 200 voltage, then you have to use 2 capacitors. and this is the driver board. So here from the microcontroller we will receive the signal to this board. So from this the signal will move to the driver, all the each and every driver. So here this is the driver circuit for one MOSFET. Similarly this second MOSFET. This is the third one and fourth one. Similarly, up to 6 drivers will be there, and the first white color IC is called the optocoupler. So here we have used TLP250 IC to get the to provide the isolation. And the second thing is the totem pole amplifier. So common emitter configuration amplifier. So it will give the maximum current whatever you feed the power to this driver, because driver also needs a isolated power supply. Right, so this is the here we have to feed the isolated power supply. So from this pin we have to feed the power with the complete isolation. So because this inverter, see here we have to feed the pulse at this is the gate pin and then source pin, right? So this pin is different from this point, because if you keep common power supply for all the drivers, so this source and this current, this point and this point will get short circuited. So that should not happen, right? So for that only we are asking that separate power supply for the each and every drivers. And Arduino controller. So here for this one we took Arduino Uno board. So this is a very basic board for powertronic applications. You can kickstart the your research from this point, from this part. So this is this board has some USB connector, power connector, on-off switch is there, and reset switch is there, and the GPIO almost 15 GPIOs are there. So we can use anyway we are going to use only 6 PWM only, right? So from this board is compatible for our applications. And now we have to configure our output. How much facility we are going to take from the microcontroller. See, our aim how to generate a code for 10 Hz or 9 to 90 Hz. So only thing we are going to generate a 6 pulse with PWM for this particular frequency, right? So how we can generate a PWM from this board. So before that we have to understand the pin, what all the pins needs to be connected with the microcontroller. See, actually I am going to take a MOSFET 1 for the PWM 1. So for this MOSFET from Arduino microcontroller I am going to take a pin number 4. Right? Similarly for MOSFET 2 pin number 5, MOSFET 3 pin number 6. So like this we are going to connect it, right? And how to kickstart the project. So here first we have to initialize the port. So as we know that Arduino microcontroller has entire components or entire ports are available. So it will be initially open end. So either it may be a high, default high or default low. So now we need a PWM, right? So we have to assign all the pins as a default low pins, and we have to assign the pins as a PWM pins. For all the pins needs to be there, and we have to take a lookup table. See here, this is the lookup table. This is the lookup table. So for the mode 1, let us take, this is the first cycle. Let us consider this is the mode 1, and this is mode 2, mode 3, mode 4, up to mode 6, right? So after, what will happen after the mode 6? Again the mode 1 will take place, right? And mode 2 will take place, right? So similarly it will continue. After the mode 6, again the mode 1 will take place. Right, so this is the lookup table. So from this lookup table, we have to assign the PWMs, and we have to call the main functions. So that function will will call the lookup table and wait for the some time delay, and it will wait till if you are pressing the reset. Suppose if you press the reset, then the program will continuously comes out from the main function. So otherwise, it will rotate within that loop itself. So continuously we can get the output. So now actually this program will help you to generate a basic pulse width modulations. Again from this, how we can increase the feature of this project, we will discuss in the end of the sessions. And so this is the hardware code. So for this one, for Arduino code, we are using that Arduino IDE. So initially we will consider the pulse 1 for the PWM1 and then pulse 2 for the PWM pin number 5, and similarly we have a pin number, right? So 9 pins, 4 to 9 pins we are going to use. And so initially we have to either these are the port identification assignment. So all the pulses, see here the pulse 1 to 6. So as a we are going to assign as an output port, not an input port. And see here, this is the mode 1 operations. So during the mode 1, pulse 1 and pulse 2 is in on conditions. So mode 2, pulse 2 and 3. Mode pulse 1 and pulse 6 is the high state. So rest of the things are the lower state. So let us consider this one. See here, mode 1, this is the pulse 1, and similarly pulse 2, and 3, 4, 5, 6, up to 6, right? So during this mode 1, pulse 1 and pulse 6 only in the high state. And similarly, rest of the things are the low, and the pulse 6 is high state. And the second mode, pulse 1 and pulse 2 is high, the remaining are the low. Similarly, mode 3, pulse 2 and 3 is high, rest of the things are the low. And again 3 and 4 is the high state, rest of the things are the low, right? So like that we have to generate. See here, so till mode 6 we have generated the lookup table. And again, see the idea is we have to take a continuous loop, right? So you can get run the loop for the 6 modes itself. Otherwise you can write a lookup table for 2 cycles, 2 operating cycles, right? So in this program we took for the 2 operating cycles. So these are 2 operating cycles, 7, 8, same actually again in the 7th lookup table is the mode 1 lookup table. Similarly mode 6 till mode 6. So up to 12th table will be there. And now this is the main function. So here we will call the first lookup table and wait for the delay. So how much delay we have to wait? So based on our frequency. Suppose if you need a 50 hertz frequency, then you have to divide it into you have to convert to that milliseconds. So 1 by 50 is equal to 20 milliseconds. So how many numbers of modes are there? So 6 modes are there. So how much is the time for each and every mode? 20 milliseconds divided by 6. So in that case 3.3 milliseconds, right? Suppose if you need 60 hertz, then again it should be 1 divided by 60. So somewhere around 18 something like that, right? So again if you divide it into 6, then again 2.3 milliseconds something like that will be there. So for that only we have to keep this as a delay. So now we have to call this delay. So this is 2.8 milliseconds. So here we have mentioned the delay microseconds. This is a subroutine. So due to that microseconds delay, so here we have used 2800. Suppose if it is 50 megahertz, here we have to use 3300 milliseconds, right? So just to save the code, and then if you download to the hardware, then we can take output from the hardware. So this is a very basic code. You can download the code from our LMS portal. And again, today is the last day to enroll into the internship option. You can check it out. And yeah, so now the code is ready. So now we have to go for the hardware demonstration. See, actually I have found all the hardware and then I took a video. So now let us verify the hardware, how the things have happened, because actually it needs more spaces. The camera is so it's not an easy job to show the demo in this live session. So I have took all the videos. Let us discuss one by one. See here, this is the 4 models are there. First one is the transformer, and this is the measurement unit, so the DSO, and here this is the transformer for the input, that is rectifier input, and this transformer is for the power supply input, and this is the driver, this is the Arduino board, and this is the driver module, and finally this motor is connected to the inverter output terminal, right? And so now we download the code from the laptop to the microcontroller. So now we are checking the pulse 1. So this is the pulse 1. So we are receiving the pulse at the DSO side, right? Similarly, we have to verify all the pulses. So this maximum output voltage of the pulse, all the pulses will be 5 voltage. But as per our theory, the MOSFET needs a more voltage than the 5 voltage. So now we have to feed the same voltage, 5 voltage, to the driver board. So if you power up the driver board, so now we can measure the output voltage of the driver up to 12 voltage. So because we are going to operate, we are going to feed the power 12 voltage DC only. So this is the 12 voltage DC output power. Output of the driver pulse. So this pulse only going to turn on the MOSFET. Again here the MOSFET 8.4 voltage is enough to start the drain current to the source. But sufficient voltage will be the 12 voltage. So you can feed the voltage up to 18 voltage. Not more than that. So 18 voltage is the maximum get to source voltage. So again it depends the driver data sheet, particular MOSFET data sheet. And so now the gate voltage we have verified with the CRO, right? Sorry, DSO, right? And so now if you connect if you power up the power supply transformer, so this MOSFET will convert the DC voltage based on the triggering pulse which we have downloaded to the microcontroller. So the motor will start to run, right? Here this again detailed demo video is also available in our LMS portal. You can check it in our see here. So we have powered up the power supply. So now the motor started to rotate. So that rotation of the motor we can measure with the tachometer. See here now the frequency is very low. So about 200 RPM is we are receiving. So now if you change the X in the microcontroller code, see if you change the code, see if you see here, if you reduce the time period at here, then we can get a increased frequency. So the idea is if you run the machine at a rated speed, then with the rated, you have to apply the rated voltage and the rated frequency. So for the 50 Hz here you have to apply 3.3 milli, that is 3.3 milliseconds. Right? So let us go for that next demo. Again, it's a continuation. So now here let us check different frequency, different speed. So here about low frequency about 270 RPM is running, and if you change the speed by feeding the delay in the software code, again we can get the maximum speed. That is, we can increase the speed of the induction machine. So now again we have changed the time delay. So let us check. So now the time delay changed. Now the speed is motor is started to running at somehow higher speed. See now earlier it was the 270, now it is a 750 RPM. So again further if you want to increase the speed, then there you have to go in the code, you have to change the delay time itself. So just only one line you have to change, then we can get a various output. Yeah, so here again further the first frequency has been increased. So now the speed of the machine is about 850, 832, something like that. So it will reach maximum level. Further, if you increase the speed, frequency, then we can increase the speed, because the speed, induction motor speed is directly proportional to the input supply frequency. So this is the hardware demo. So further, how we can increase the facility with this one. So here, for each and every speed, we have manually we edited the code, and then we are downloading the code to the hardware, right? So instead of this facility, we can keep 2 input switches, and we have to add the program. We have to add that logic in the program. So if we keep increasing the switch, then we can increase the speed. And similarly, if you reduce the switch, then we can reduce the speed. So like that, we can add that facility. And the same thing can be implemented with IoT, so that we can enlarge the facility. And second thing, we can add speed measurement unit. So with the help of magnetic sensor, we can sense the speed of the induction motor, and then we can display the speed in the IoT cloud. Similarly, we can add automations. That is a cooling system automations. So cooling system automation and then fault automations. So whenever the motor continuously running, so during that period, the motor will get heat. So for that one, we have to add one temperature sensor to sense the motor temperature. So if the motor temperature increases certain level, then we have to turn on the cooling fan. So that is called the cooling system automation. Similarly, fault rectification. So we have to keep 1 or 2 current sensors and then voltage sensors to sense the voltage levels and then current level. So from this also we can add, and then we can finish the final year projects.